including the comparison between freshmen and experienced engineer, challenges we have every day. I will also address the rigorous simulation versus common sense. And I have included 3 examples. And finally, I would like to give some recommendations. The first topic is what's the difference between freshman engineer versus experienced engineer. If I have the question about what's the size of a pipe for 100 cubic meter an hour water, so we have flow of 100 cubic meter an hour, and we have to size the pipe. Here we have the junior engineer, and if the velocity inside the pipe is 10 meters a second, then the size should be 59 millimeters as a diameter. And we can calculate. Or if the velocity is 100 meters a second, then 90 millimeters. It's very simple. Here we have experienced engineers, and he said the diameter should be 130 to 190 millimeters. So he's very specific. Why? Because he knows the velocity must be 1 to 2 meters a second for liquid inside a pipe. The feature of experienced engineer, he can estimate the appropriate size of equipment without computer. He can check the detailed calculation without computers. Experienced engineer has the knowledge of standard values. First question to ask, or quick calculation, or meaning of the parameter value. So in a sense, we can say that the experienced engineer has common sense of process design. And this is the topic I would like to cover during my presentation today. Let's talk about the challenges. If we have enough number of experienced engineers in our company, we have no worry about our future. What's the situation? This was taken from the statistics from the Japanese government, so unfortunately I don't have the Korean figures. This is a trend of the population for 0 age to 14 years of age. Back in 1980, Japan had almost 25 million the people. But we have the trend of the reduction, and 2020, in 20 years time from now, we will have a shortage of the potential engineers. So if we compare the population between back in 1980 and 20 years later from now, population of 0 to 14 years old, which I define the source of future engineers, will decrease to 50%. That's a big problem the industry is facing. To worsen the situation, this is not the only the problem we have in Japan. Every year, our government is taking the questionnaire about the people's interest in science and technology. So the question, one of the questions was, are you interested in science and technology? So during this period, starting from 1980 to the last year, this is a figure. For all ages, we have a reasonable number. More than 50% are interested in the technology. But the important fact is here, 20 years ago, younger people were very interested in science and technology. But these days, almost half of the people who are interested in the science and technology, we have only 50%. So the situation is there, the human resources will be reduced further. So this is one of the biggest challenges we have in Japanese industry. Maybe you have the similar situation here On the other hand, let's talk about your concrete expectation from you. I don't know how many of you today in this room are from the industry and how many of you are students. But how many years will your boss be patient for you to accumulate experience? Dr. Ogawa mentioned the importance of accumulation of technology, but it takes time. And how many years do you think your boss will allow when you join the company? And typical answer by the Japanese manager, 5 years. Or if the manager is aggressive, he would say 3 years. So, the typical company expects us that we develop our own expertise within 5 years after joining that company. So comparing to that expectation, I would like to talk about the situation about today's engineers in Japan. Maybe applicable to here. Yeah. I am conducting some questionnaires regarding course design, consisting of 100 common sense questions. And I started these activities approximately 6 months ago. And I have conducted surveys more than 50 engineers from the top-class chemical companies in Japan. And the answer was categorized into 3 areas. I know well, I'm not sure, I've never heard of. One of the typical questions was, do you know how to use triangle diagram? Do you know triangle diagram? When we design the liquid extraction for ternary system, we have to use triangle diagram. And we learned actually at the university. This is the result. So the good news is that a little more than 50% of the engineers said that, well, we know well. The bad news is almost 50% of the people say that I've never heard of or I have never used since joining the company. This question was not the most difficult one. What about this one? Meaning of parameter G of Antoine equation. In the morning I explained the application of the Antoine equation for vapor pressure. And for Antoine equation we have 3 parameters usually, A, B, and C. And I asked, the question was, do you know the meaning of the parameter B of Antoine equation? And then suddenly their success rate of the answer dropped to less than 1/4. And many people are uncertain about their knowledge. The next typical question is, I hope you know relative volatility. If the relative volatility is 2, do you think it's a difficult separation or not? This is a very important, actually, question to understand. Maybe you can skip these 2 questions, but if you work in the process industry, you cannot escape from this type of question. We have to make a judgment if this separation is easy or difficult, surveying the physical properties. So this is a very important question, but unfortunately, only a handful of people say that we know that. So most of the people asked about this question said, well, I'm not sure, I have never heard of this. But this is the reality of today's engineers in Japan. So we have not only future but also concern over today. That's the situation. So today's challenges and needs for training, there's a huge gap between expectation and reality. That's what we are facing today. And we also have the concern over the future of human resources, as we saw about the trend of the population. So these are the reasons why we need to train our engineers. Coincidentally, Dr. Ogawa also emphasized that it's very important for us to train engineers, which is true not only for process control, but also the process design as well. We have to train engineers so that, one, they can make the best use of process simulator if we can use a process simulator. And they should be able to design processes without simulator if we cannot use process simulator. There are many processes these days which we cannot use process simulator for. And as long as we are engineers, we have to come up with the right design, even with or without process simulator. So for these two reasons, we have to pay a lot of attention about training of the engineers. Now I would like to give 3 examples about rigorous simulation versus common sense. I'm not saying that rigorous simulation is not necessary. On the contrary, I strongly believe that we have to use process simulator for better design. But in order for us to have the right design, we also have to have the common sense. And we would like to see this slide now. Before getting into the examples, this is a brief description of the terminology. Many design options are theoretically feasible, but only a small number of designs have survived and implemented as a real plan. They have technical and or economical reasons why we select the design. The knowledge related to them are accumulated in each experienced engineer after a long trial and error effort. They are called, well, these knowledge are called rule of thumb, heuristics, back of the envelope calculation, well, common sense of process design, which are all related to conceptual process design. So we are talking about conceptual process design. For the detailed calculation, we definitely need process simulation. But if we talk about conceptual process design, what should we do? That's the topic we are focusing on. The first example is distillation warm-up. We have a dialogue between the engineer and the manager. And the problem is the separation of also and other dichlorobenzene. These two compounds have a boiling point at 180 and 174 degrees. So the boiling point difference is only 6 degrees. So please imagine how difficult it is. The engineer said that, well, I used Aspen flux to calculate the distillation column. It looks the separation is not easy. Should I continue the case study, or do you have some suggestion? So he comes to you and asks this question. A possible answer A. If you are very technical, probably this would be your answer. Let me check your calculation first. Can you send me the simulation file, please? Alternative answer. Run more case studies. And theoretical 50, 100, 150, and reactive ratio 10, 50, and 100. Sometimes we have this answer. The boiling point difference is only 6 degrees C. Distillation is not practical. Make research on other separation. So these are 3 possible answers. So actually, also part dichlorobenzene production is usually carried out using the crystallization. Some of you may know this. Actually, no distillation was employed for this process. Then why 6 degrees difficult for distillation? Why? Of course, we could come to this conclusion after many trials using the regular simulator. But there are another way. This equation is very simple. Number of stages, actual number of the stages of the column equals 1,350 divided by difference of boiling point. It's very easy. So if the temperature difference is 10 degrees, then 135. Can be 135, maybe 100. But the point is, if you know this equation, it's very quick to calculate the difficulty or easiness of the equation. Who found this? Rigorously speaking, we need to understand what are the components and their VLEs. Target theoretically to calculate the number of the stages. So rigorously speaking, there's no answer to this problem of 6-degree separation. However, what is interesting is existing columns have common features. That's what Mr. Kawai said, Mitsubishi Kasei, back in 1987. He described molecular chemical engineering for force design. And he used this example. At that time, I was very impressed with this one. And I also checked his equation with my columns I worked for at that time. And I found, of course, this is not rigorous, but if you are interested in the conceptual process design, this equation that gives me enough confidence. So if the temperature difference is only 6 degrees, it's not necessary to spend more time on the calculation of distillation. We need to change our calculation and start doing the another thing. So common sense as quick calculation methods from experience. Second topic is to install steam turbine or not. Suppose you are thinking of the energy saving of your plant site, and maybe someone asked this question. Do you think it's a good idea to install steam turbine to save energy of my plant site? And here we have some consultants. He will say, maybe. But let me ask this question. Do you know the steam demand and electricity demand on your site to answer your question? So he said that, well, the total steam consumption is 300 tons an hour, and electricity demand consumption is 100 megawatts. Then the consultant would say, my suggestion is that you consider gas turbine first, instead of the steam turbine. You can also study steam turbine to combine with gas turbine. Where does this consultant get this information from? Why does he think so? This is a rough diagram of the steam turbine cooking cycle. We have the boiler producing the high pressure steam. We have steam turbine, and we generate electricity here by producing the low pressure steam. And all the steam turbine system produces not only steam but also electricity with the ratio of 6 to 17. That's the fact we have in industry. We have also other combinations. Well, this is the gas turbine configuration. We have air here, compressed, and inject fuel, burn, expand, then to generate electricity. We can also utilize the heat from the exhaust gas to recover heat as process steam. Gas turbine usually have the steam to electricity ratio to 2 to 4. The third one is the cogeneration. So we have gas turbine and the boiler. We have second the turbine. So we have generator here and heat. In this case, the characteristic number of the steam to electricity ratio is 1.5 to 3. So if you select the configuration of the energy saving, the equipment, you have to use a certain ratio of steam to electricity. That's the fact we have in industry. So if we plot steam to electricity ratio on this the axis, the steam turbine covers wide range, but relatively higher ratio of steam to electricity. Here we have the different the zones for gas turbine and combined cycle. What is interesting is to plot the existing sites on this diagram. You may also want to do it with your own the plant data. This is a survey I made in Japan and found this. In case of refineries, the figures of the steam to electricity ratio is more than 10. So that's why we see many steam turbines in the refinery plants. But if you have to deal with chemical plant has a different nature. And usually this covers the lowest 2, which I know, and highest 8. So this is the range. So if your chemical plant has a higher ratio of steam to electricity here, then it's quite reasonable to install steam turbine. But if the ratio is very low, we have to consider these two options. So suppose we have chemical site around here. So we have to start the energy saving here. So the first, if we start the energy saving project, usually steam is easier to reduce than electricity. So firstly, we introduce side steam turbine system to reduce electricity cost, which is reasonable because the steam turbine has a fit to this range. And then if we reduce the energy steam consumption, this ratio will be reduced to this direction. So the next, we need to consider to install gas turbine and combined cycle to reduce the electricity further. Finally, we reach this point, and with the current technology available in the market, unfortunately, this is a kind of the limit we have. So if your plant site has this number, maybe energy saving is not the best R&D thing to investigate. So this is common sense as a procedure and figures from experience. The third example is related to capturing the image. There's a researcher saying that we conducted experimental study with a simulator and found A, this reaction is in first order, and B, the rate constant is 10 inverse of minute. And then there's a question. Is it a fast reaction? And he doesn't know. He ran the simulator, and he understands the figure, but he doesn't understand the meaning, or he cannot interpret this figure into his real image of the process. Possible answer. All of us learned this at the university, so I hope you recall this kind of calculation. First, we learned that the unit is very important, dimension. So look at the unit of K equals 10 inverse of minute. And the inverse of minute is not familiar to me, but minute is a familiar unit. So take the inverse of minute. Then we obtain 0.1 minute. So this should mean something related to the rate of the reaction. So 0.1 minute is 6 seconds. So this sounds like a fast reaction. But of course I should compare it with other time constants such as residence time of the reaction. If the residence time of the reactor is 1 minute, then I can expect probably all the materials will be converted. So we cannot make a judgment solely by this figure, but we now have much better understanding about this figure. The second answer, more theoretical answer, is possible. This is the differential equation of the first order reaction. Then after resolving this, we obtain this. And we remember that half time is calculated by this the formula, and then 2 divided by the time constant, then 4.2 seconds. So 4.2 seconds is the half time of this reaction. So in 4.2 seconds, the 50% of the feedstock will be converted into the process. So it's very, in a sense, it's fast. I usually calculate this time to E inverse. Do you remember E? 2.713 something. Of course, E is not 2.5, but if we assume 2.5, then this is 40%. So I usually just take the inverse, assuming that, well, time to 40%, which is at 6 seconds. So this gives me enough confidence how to interpret the experimental data. Of course, we need other time constants for comparison. So don't jump into the conclusion that this is just reaction, but we now have better understanding. So this third one is the common sense from theory, physical chemistry. So the common sense is mostly related to the experience, but not always. If you study, well, chemical engineering or physical chemistry, these basic engineering subjects they give us many useful actually information about this kind of thing, and we learn some of these the knowledge at the university. Finally, the recommendation. Common sense, rule of thumb, heuristics, back of the envelope calculations are critical for correct judgment to complicated calculations. Their sources are not only experience but also physical chemistry. And the third one is very important. They are quite essential for complement to process simulation for conceptual process design. As I said, process simulation is very important. But in order to make a correct judgment, it's also very important to have some ideas to make a judgment about the result of the process simulation. So this is what I call rule of thumb or conceptual process design, or the common sense. Experimental work is very important, and also modeling and simulation are complementing this experimental work. We can derive a new finding from the experimental work. And then by working with modeling software or simulation software, we can have a prediction from the initial model. Then run this experiment again. Additional data we will obtain. We refine the model, etc. So we can continue to improve this model. But at the same time, it's very important to check the result with rule of thumb. And rule of thumbs are everywhere around us, and we have to pay attention. What are the rule of thumbs important to my task? Okay, this is the end of my presentation. Thank you for your attention.